Hello guys, welcome back to my channel. And as you know, I have restarted my high school calculus playlist. So in the last video we talked about implicit differentiation. This video is sort of an offshoot of that previous video of implicit differentiation. So if there are any of you who don't know what I'm talking about, if there are any of you who don't know what implicit differentiation is, I would recommend you to click on the card that I have provided, I think about now. But for my regular viewers, let's get to it. So in the questions that we are going to discuss today, we have a type that's called variable raised to variable. So in the variable raised to variable category, I'll first give you a general overview of what we're going to majorly do in this video. So say you have a function x to the power of x, and they want you to differentiate this with respect to x. So you have a variable raised to, in this case it's the same variable, but this exponent can be any other variable. It can be a function of y as well. So how do we go about with these questions? Because we did not deal with certain kind of mixed variety of functions. So since we have a power, power actually asks for the natural log. So if you see a power anytime, you can either use the power rule. If the power is a number, then you can use the power rule of differentiation. But if it's a variable like this, say it's a variable to the raised to variable category, you let this equal to some other letter y in this case, and then you take the natural log on both sides. When you do that, you have a natural log of y being equal to the natural log of x to the power x. And one of the properties of logarithms in general is, say you have a log, this can have any base. Natural log has a base e, we can have any base. So if you have a natural log of, in this case, a to the bth power, you can write this as b times the natural log of a. So you can sort of multiply the natural log of the base with the power. So that's what we are going to do. We have natural log of y is equal to x, because that's the power, times the natural log of x. Well, now it seems like it's a great time to differentiate, because natural logs are one of the easiest functions to differentiate. So now we're actually going to differentiate. So when we do that, we have d over dx of the natural log of y being equal to the derivative of x times natural log of x. And now we just learned to differentiate the natural log of y, or any function of y, in yesterday's video of implicit differentiation. So this is going to be 1 over y times dy over dx. Never forget the dy over dx. And now we have to use the product rule. So x times the derivative of the natural log of x plus the natural log of x times the derivative of x with respect to x. So now we have dy over dx being equal to y times x times the derivative of natural log of x is 1 over x, plus derivative of x is 1, so you just have a natural log here. These x's are going to cancel out. And what's y actually? What's y? Y is just the original function that we started with, right? So you plug that in, because y is something we introduced and the question never gave us anything like that. So resubstitution, y is x to the x, y times, these x's cancelled out, so we have 1 plus the natural log of x. So that is exactly dy over dx, and that's what we had to find. So I hope you got a general sense of what we are up against in this video. Let's do a set of examples now, which ideally are going to get complicated and complicated. So now we have a function of x, f of x, being equal to 3 plus x divided by 1 plus x, but raised to 2 plus 3x power. So variable raised to variable, right? Because there's an x in the power. And now they want us to find not dy over dx, or in this case f prime, but f prime of 0. And if you remember my notation correctly, f prime of x is just the derivative of f of x with respect to x. This is just Newtonian notation. So f prime of 0 is basically finding the derivative function and then plugging x equals 0 in the final derivative function. That's when you get f prime of 0. In other words, it's the slope of the tangent at x equals 0, if you want to think about it geometrically. And I have explained this concept in my differentiability videos, so you might want to revert back to some old videos of my playlist if you don't remember this concept. So as I said, as we did with the last example, let's take the natural log on both sides. So the natural log of f of x is equal to, we can bring the power down, 2 plus 3x times the natural log of the base 3 plus x divided by 1 plus x. Now remember another natural log property. So let's write the left hand side as it is. We have 2 plus 3 times x. This can be written as the difference of two logs. So we have the natural log of 3 plus x minus the natural log of 1 plus x. And we can write these as two different expressions. So we have 2 plus 3 times x times the natural log of 3 plus x minus, just a distributive property, 2 plus 3x times the natural log of 1 plus x. And now, since we have everything in terms of natural logs and normal functions, now is a good time to differentiate with respect to x on both sides. So you end up with, when you differentiate this, you get 1 over f of x times the derivative of f of x, right, by the chain rule, which can be written as f prime of x, Newtonian notation. And here we have to use the product rule. So we make 2 plus 3x weight while we differentiate natural log of 3 plus x, and we're making the natural log of 3 plus x weight while we differentiate 2 plus 3x. And don't forget this other part. We're doing the same thing essentially over here. We are letting 2 plus 3x weight as we differentiate the natural log of 1 plus x, minus the plus and a minus will make a minus of, make the natural log of 1 plus x weight while we differentiate 2 plus 3x. I'm just showing you all the steps for the first example. So this becomes f prime of x divided by f of x being equal to 2 plus 3x as it is. The derivative of natural log of 3 plus x is just going to be 3 plus x, because by the chain rule the derivative of 3 plus x is just going to be 1. I hope you can see that. So and on this side we have the derivative of 2 plus 3x is just 3, right? Whatever term is multiplied with x, it's just that term, because 2 becomes 0 on differentiation. So we have 3 times the natural log of 3 plus x, and now this minus 2 plus 3x divided by 1 plus x minus the derivative again is 3, so negative 3 times the natural log of 1 plus x. So now we have an expression for f prime of x. Why don't we plug in x equals 0? So I'm saying let's put x equals 0 because that's what we wanted to find. We wanted to find f prime of 0. So we need to plug in 0 everywhere in the place of x. So we need to find f of 0, and we have the function f of x given to us, so let's plug in 0 over here. So f of 0 is just going to be 3 plus 0 divided by 1 plus 0 is just going to be 3 raised to 3 times 0 is 0, so we just have 2, which becomes 9. So f of 0 is 9, we know that now. So we have f prime of 0 divided by f of 0, which is 9, being equal to 2 plus 3 times 0 is 2 divided by 3 plus 0 is 3 plus 3 times the natural log of 3 plus 0, which is 3, minus, we just have a 2 here, the denominator is just 1, minus 3 times the natural log of 1. Natural log of 1 is going to be 0. And if you do some simple algebraic manipulations, taking 9 on this side, doing some addition subtraction over here, you finally end up with negative 12 plus 27 times the natural log of 3. So that's our f prime of 0. So that's the slope of the tangent line of the function f of x that we defined above at x equals 0. Nice. So let's do another proving question like we did yesterday. I think we did a bunch of proofs yesterday. So this one says if we have a function y being equal to square root of x raised to the square root of x, which itself is raised to the square root of x, and this process of raising to the square root of x power is going on till infinity. It's going on till infinity, and we have to prove that x times dy over dx is going to equal y squared divided by 2 minus y times the natural log of x. Well, instantly looking at the arrangement of y, it's variable square root of x raised to itself, so variable raised to variable. So what are we going to do? Natural log, right? So natural log of y is going to equal whatever the power was, square root of x raised to square root of x raised to square root of x going on till infinity times the natural log of square root of x. And what's this part? This part is again y, right? Because if you remove one square root of x from an infinitely long series, it doesn't matter to it. It's just going to remain the same thing. So we have natural log of y being equal to, this is y, you can just draw parallels, times x, square root of x is x to the half power, so we can bring the power down and write this is natural log of half of the natural log of x. Now is a great time to differentiate, because we've gotten rid of all our crazy powers. So we're going to end up with 1 over y times dy over dx, implicit differentiation, and now product rule. So half as it is, first I'm making y weight as I differentiate the natural log of x, plus natural log of x times the derivative of y is dy over dx. So we have dy over dx times 1 over y being equal to, derivative of the natural log of x is 1 over x, so we have half of y over x plus half of the natural log of x times dy over dx. Let's collect these dy over dx terms. So we have dy over dx being equal to 1 over y minus half of the natural log of x being equal to half of y divided by x. Now we can actually take the LCM of this dy over dx multiplied part. We get dy over dx. Taking the LCM, we have 2 minus y times the natural log of x divided by 2y being equal to half of y per x. So the 2's are going to cancel out. We have finally dy over dx is equal to, we can take the x on this side. We have this y will get multiplied with the numerator there. We have y squared divided by 2 minus y times the natural log of x. And that's exactly what we had to prove. So hence proved. So now we have to differentiate sine of x, which is raised to the natural log power, but that's not all, plus x raised to 1 over x power. Now, variable raised to variable, after you identify that, you call this collective sum y. And now notice that we have two separate variable raised to variable that are being summed together. So I would like to, differentiate them separately. So I'm calling this v and I'm calling this w. And since we have to find dy over dx by the sum rule, the addition property of derivatives is going to be dv over dx plus dw over dx. So it's going to be the sum of individual derivatives of v and w with respect to x. So let's differentiate v first, and w we'll differentiate separately and then add them back together. So when we have dv over dx, that's going to be the derivative of sine of x to the natural log of x power. So, and before differentiation, let me remind you that we have to take the natural log on both sides. So we have the natural log of v being equal to the natural log of x, that's because that was the power, times the natural log of sine of x. Now is a good time to differentiate with respect to x. So we have 1 over v times dv over dx being equal to product rule now. So we have natural log of x times the derivative of the natural log of sine of x plus the natural log of sine of x times the derivative of the natural log of x. 1 over v times dv over dx being equal to the derivative of the natural log of sine of x is just going to be the cotangent of x, because this is going to be by the chain rule cosine of x divided by sine of x, which is the cotangent of x. So cotangent of x times the natural log of x plus the natural log of sine of x. The derivative of natural log of x is 1 over x. So dv over dx is now taking the v on that side. What was v? It was just this initial expression, right? So sine of x raised to natural log of x times cotangent of x times the natural log of x plus the natural log of sine of x divided by x. So that's our dv by dx. Time to do our dw by dx. So as we defined, we have w being equal to x raised to the 1 over x power. So now again variable raised to variable, take the natural log on both sides. We have 1 over x times the natural log of x, and now is a good time to differentiate with respect to x on both sides. So we have 1 over w times dw over dx being equal to, again, product rule. So we have 1 over x times the derivative of the natural log of x plus natural log of x times the derivative of 1 over x. This is just 1 over w times dw per dx being equal to natural log of x is going to be, when differentiated with respect to x, is going to be 1 over x. So we have 1 over x squared because of this. The derivative of 1 over x is negative 1 over x squared. So we have negative natural log divided by x squared. We can just have a common denominator. So 1 minus the natural log of x divided by x squared. So dw over dx, taking the w on that side, w is just this x to the 1 over x power times 1 minus natural log of x divided by x squared. And if you remember what we had to find dy over dx, and what was that going to be? It was going to be dv over dx plus dw over dx. So plugging in all these crazy terms, we have dy over dx being equal to, first we have the sine of x raised to the natural log of x times the natural log of sine of x divided by x plus cotangent of x times the natural log of x, and then we have the dw over dx term plus x to the 1 over x power times 1 minus natural log of x divided by x squared. So it's a pretty nasty expression, but at least we got our problem solved, right? Nice. So now we have to again find dy over dx. And this time we have this equality that's established as follows: cosine of x raised to yth power is equal to cosine of y raised to the xth power. Now let's go ahead and take the natural log on both sides. So we have y times the natural log of the cosine of x being equal to x times the natural log of cosine of y. Again, product rule on both sides. If we differentiate with respect to x right now, which is a great time to do so. So we have y times the derivative of the natural log of cosine of x plus the natural log of cosine of x times dy over dx is equal to x times the derivative of natural log of cosine of y plus the natural log of cosine of y times the derivative of x with respect to x. So the derivative of natural log of cosine of x is going to be negative tangent of x. If you want to do that on a piece of paper, you can, but you know, these are pretty standard results because we come across them a lot in integration. So you have negative y times the tangent of x plus the natural log of cosine of x multiplied with dy over dx is equal to, we have a negative x times, this is going to be a tangent of y, but don't forget the dy over dx of implicit differentiation. This is going to be 1 plus the natural log of cosine of y. You know, we can collect the natural log, the dy over dx terms. You have natural log of cosine of x plus x times the tangent of y being equal to natural log of cosine of y plus y times the tangent of x. And to just obtain a dy over dx, we divide both sides by this part, and we get natural log of cosine of y plus y times the tangent of x divided by the natural log of cosine of x plus x times the tangent of y. So this was a really nice problem. I hope you appreciated it. And let's do the final problem of today. We have x raised to y times y raised to x being equal to a raised to the bth power. So again, natural log, right? Variable raised to variable situation. Natural log on both sides. We have natural log of x to the y power times y to the x power being equal to natural log of a to the power of b. We can split this up by the property of the natural log, by this property. Natural log of a times b is going to be the natural log of a plus the natural log of b. So the natural log of x to the power y plus natural log of y to the power x. This we can just write as b times natural log of a. We can write this as y times natural log of x plus x times natural log of y being equal to b times natural log of a. And when we realize we can't simplify any further, that is when exactly it's a good time to differentiate with respect to x on both sides. So then we have product rule here. Y times the derivative of natural log of x with respect to x plus natural log of x times dy over dx plus x times the derivative of natural log of y plus natural log of y times the derivative of x with respect to x, and the derivative of this thing b times natural log of a is going to be 0 because b and a both are constants. Natural log of b times natural log of a is differentiated is going to be 0. Now as always we collect the dy over dx terms, but we still need to differentiate this properly. I didn't see that, sorry. So we have y over x plus the natural log of x times dy over dx plus x over y times dy over dx. This is going to be 1 plus natural log of y being equal to 0. Now let's collect the dy over dx terms. So dy over dx is going to be natural log of x plus x divided by y is equal to, we can collect a negative here, y over x plus the natural log of y, because that's going to be common when we take this on the right hand side. And now just making dy over dx the subject of the equation, we have negative y over x plus natural log of y in a bracket divided by natural log of x plus x over y. So again, using natural logs to bring the power down when we have a variable raised to variable situation, you might have noticed is an excellent and elegant way of solving these derivatives which would have otherwise not been possible for us to solve. So I really hope you enjoyed this video, guys. Please like, share and subscribe. Recommend me to your friends or people who really want to learn high school calculus. I know I wanted to learn high school calculus on my own way before high school. So if there are nerds like those, please forward it to them. And stay safe. Peace out.